This video is from chapter 14, which is about the basics of the specificity of sugar metabolism. So there's other parts of sugar metabolism, but they're a little bit more generic. And this is just specifically the part of metabolism that only sugars go through. So the breakdown of carbohydrates is all going to be based around glucose. So we have other carbohydrates. We might have fructose, we might have galactose, we might have polysaccharides, we might have disaccharides, but generally speaking, what we're going to do is have a way to break down glucose, and then everything else will be broken down in basically by sort of either converting it to glucose directly or to something in that pathway. So if we have dietary polysaccharides, the majority of these that we talked about are actually made of glucose, right? So amylose, amylopectin, glycogen, those are all made of glucose. So what we do is in our digestive tract, it breaks down all of these little bonds between the glucose monomers, and we end up with glucose. And then glucose, the first portion of glucose metabolism is called glycolysis, and that is what we're going to focus on today. Glycolysis is going to result in pyruvate, or rather 2 molecules of pyruvate. And then pyruvate will be further broken down into carbon dioxide and ATP, and that will be in a future chapter. If we have dietary disaccharides, for instance, sucrose, again, what we're going to do is we're going to break it down in the digestive tract to glucose. And if we have another monomer like fructose, that also obviously is going to break down, right? So this is glucose and this is fructose. So when we break this bond, we get glucose and we get a fructose. If we have a different disaccharide, you might get galactose or something. And then fructose metabolism is, instead of having a whole separate way of breaking down fructose, instead it's going to merge with the glycolysis pathway at some point. We're not going to talk specifically about that this term. That will be in the second term. So what we're going to talk about really here is this section. So glucose to pyruvate. So again, glycolysis, just the first phase. It brings us to pyruvate. So here is the structure of pyruvate. It is basically, it's a methyl group, or rather it's a ketone that has a methyl group off one side and a carboxylic acid off the other. So glucose has 6 carbons, pyruvate has 3 carbons, and so we have 2 of them. One thing that I would suggest as we're going through metabolism is really focus on where the carbons are and where they're going. Oxygens can come and go. We might have redox reactions, we would have water being added or something like that. Hydrogens can come and go, but if you keep track of where the carbons are, you'll be doing pretty well. So we take our 6 carbon glucose, we go to 2, 3 carbons of pyruvate. This takes multiple steps, and the whole thing is called glycolysis. In addition to pyruvate, we are also going to create, during those steps of glycolysis, 2 ATPs and 2 NADHs. So we should keep track of this. What we really want is ATP. We're also going to, throughout catabolism, make a lot of NADHs, and at the very end, we'll see what happens to those. But NADHs are also important, so keep track of what's happening there. Glycolysis has specifically 10 steps. It's going to be broken into 2 phases, and the preparatory phase and then the payoff phase, each of which is 5 steps. And so this is a figure in your book that sort of just goes through all the steps, but it's kind of, right, it's small and it doesn't have a lot of details. But what it does have is all of these structures, and it has the names of the enzymes, which sometimes can be helpful, and also the names of the organic compounds, and then anything else that happens in the reaction. So here we're actually going to use an ATP. Here we are going to create 2 ATPs. So once we've gone through it all, this is a good sort of summary. You do not need to know the names of these enzymes, although it may be hexokinase, since we've talked about it multiple times already, right? You already should know what that means. But I do think a lot of times it can be helpful, right? Because we already know what kinases are. Isomerase is obviously going to tell you that you're going to be making an isomer. Dehydrogenase tells us it's a redox reaction. So Sometimes they can be helpful, but I'm not going to ask you what the name of the enzyme that does step 4 is or something like that. So the preparatory phase, which is the first 5 steps, actually uses ATP. So step 1 is going to use an ATP. Step 3 is going to use an ATP, which is not where we're trying to go. We're trying to make ATP, but the reality is we have to sometimes use ATP to make it. Also, I guess here it may be useful to point out, step 4 is going to break into 2 different compounds, and one of those is going to go through step 5. So actually step 5 is kind of only half the things go through it. But we'll talk a little bit more when we get there. The payoff phase is going to make ATP, and it's actually going to make ATP in this step and in this step. And notice that starting in the payoff phase, we always have 2 of every molecule, and that's because we're always going to sort of judge this based on what we would get out of 1 glucose molecule. So because at this point we've broken it in 2 already, we haven't made pyruvate yet, but we've broken it in 2, so everything is times 2. All right, so this step right here is going to make 2 NADHs, and here we're going to make 2 ATPs, here we're going to make 2 ATPs. All right, so that is the reason that it makes it okay that we use some ATPs in the preparatory phase. Because the net production here, right, we used 2, but we made 4, so overall, we did still make 2. So also the net reaction here, we generally focus on glucose and the pyruvates, but we do also produce 2 NADH, and those didn't come out of nowhere. We had to start with 2 NAD pluses. The 2 H pluses also came from, right, remember when we make NADH, we make NH plus. We made 2 ATPs, which again didn't come out of nowhere. We had to make it from 2 ADPs and 2 phosphates. And we also produced 2 waters. We don't generally focus too much on how many waters we might make or use in something, since there's just so much water around. But that is, we did make those, and that's where a couple of the oxygens are going to go. The overall reaction has a delta G of negative 85 kilojoules per mole, even though we are making these ATPs already, which, right, because it's the other things must be giving off so much energy that even though we're using some of it to make the ATP, we're still negative and it's still favorable. This has it broken down so we can really see how that's true, right? So making 2 ATPs has a very positive delta G, so actually the delta G, if we don't include that, would actually be even more favorable. So that's how we get to the negative 85. All right, so now we are going to go through each step individually, and I'll tell you some important things to know about those steps, critical pieces of information or mechanisms or whatever. So step 1 is just a phosphorylation. This is done by a kinase, which should not surprise us, right? We've actually seen this reaction multiple times. This phosphorylation happens on carbon 6 of the glucose. So it makes glucose into glucose 6-phosphate. I guess this is as good a time of any. We have not really done any mechanism arrows here, so I just want to clarify, right? Just remind you of some stuff you should remember. We always draw arrows from the nucleophile to the electrophile. The nucleophile is going to be the one that does the attacking. Generally speaking, it's one that has a lone pair of electrons on it, so we always draw it from here to here. Nucleophile is generally going to be oxygens, maybe nitrogens. And then if we have a pathway, we have multiple arrows. One arrow has to then lead to the next. So we attacked this phosphate, which meant this bond needed to break. So we have another arrow. That shouldn't really be going to this oxygen. It should kind of be going here. So you can't just draw arrows every which way that are unrelated to each other. And you should also just never draw the arrows the other direction. It's just kind of convention, but we shouldn't do it. All right, so this oxygen attacks there, breaks this bond, so we are left with ADP and glucose 6-phosphate. So this delta G is pretty negative, and this reaction is highly irreversible. So this is not a reversible reaction, right? Or it's not an equilibrium reaction. This is irreversible. Once this happens, I mean, we could go back, but you would have to go maybe get a phosphatase or something to cleave this off. It is not just going to really go back. Once we've made glucose 6-phosphate, we're there. Most steps in glycolysis are not going to be irreversible. They're mostly going to be reversible, but we have sort of key steps throughout it that are irreversible to sort of keep the process going. Step 2 is an isomerization, and the isomerization is going to go from glucose 6-phosphate to fructose 6-phosphate. So the way this works is we're going to start over here. The first thing we have to do is open the ring because the isomerization reaction happens on the linear sugar. So we're just going to open up the ring. And so now this is just our linear glucose molecule. And then the second step is going to be deprotonating carbon 2. Not a particularly acidic thing, but we can deprotonate it because the electrons can move here and form a double bond and open up that carboxylic acid into an enediol. This also, it's showing you the hydrogen here, but really this arrow would just be drawn grabbing the hydrogen. So now we have this. So an enediol is a double bond with OHs off both sides. So I think the key thing to remember here is it's equivalent, right? This carb, we have a carbon double bond. Each one has an OH. So either way could happen. We could have a deprotonation. So when I draw like this, this means a base. So the base could take off this hydrogen, causing these electrons to go make a double bond. And now these electrons to go take back the hydrogen that was just lost here. So that's going to form fructose, the ketose. Now this could do the other way around though. This base could take off this proton and then this could go back down. We just go back to glucose. So this is a very equilibrium reaction. All right. Isomerizations generally are equilibrium reactions because the delta G is not going to be very different. So the delta G here is pretty close to 0. And so this is going to be a reversible reaction. So we could go back to make glucose 6-phosphate if we wanted to. So the last step is just going to be reclosing the ring, which again should all be pretty comfortable with, right? It's just the same thing we already talked about in the sugar chapter. So this isomerization moved the double bond from the carbon 1 to the carbon 2, and you'll remember when we learned about the sugars, I said fructose is the same as glucose from here down, and this is essentially why, right? Because they can be interconverted this way. So we're not going to focus too much on this, but you may be able to predict right now how fructose is going to enter glycolysis. It's going to be basically here since we've made fructose. All right, so now we have fructose 6-phosphate. Step 3 is going to be another phosphorylation. So we're going to put a phosphate on the 1 carbon. And so again, just ATP. I'm not going to draw out, how this happens every time. ATP puts a phosphate on. We had to do the isomerization first because if we had put the phosphate on the 1 carbon when it was still glucose, we wouldn't have been able to open it up. So that's actually why that had to happen first. So this has also a pretty negative delta G, and this is also irreversible. This is also called the committed step, which means once you get here, you are going to go through glycolysis. You can stop, or it's not really that you can stop, but as at glucose 6-phosphate or fructose 6-phosphate, there are other pathways you can go down. We're not going to see very many of them, if really any, in this term, but there are other pathways you can go down. But once you make it to fructose 1,6-bisphosphate, which is irreversible, you are going to finish going through glycolysis. All right, step 4 is this important carbon-carbon double bond or carbon-carbon bond cleavage step. This is between carbons 3 and 4, which we should be able to figure out because we have 2 3-carbon molecules, right? So we clearly have to break this bond. No other bond would work. So you'll notice that we've put phosphate, we have a phosphate on each one, all right, at this point. So that's probably why that had to happen first. So fructose 1,6-bisphosphate, this reaction is catalyzed by aldolase, and this actually is catalyzing a reverse aldol reaction. So an aldol reaction is when we have a carbanion that is next to a carbonyl that attacks a ketone and then forms something like this, where we have ketone, a carbon, and then another oxygen. And this, we could have an OH here, that's fine too. So a reverse aldol is going to do the reverse, where essentially this goes down into a double bond, this one gets cleaved, and we have an anion. So the mechanism for this is a little bit more complex, but before we get into that, this is a pretty positive delta G. That shouldn't be favorable. This is one of our examples where the real delta G is pretty different from the delta G standard. The Q is significantly less than 1. So, and the reason for that is the next step, step 5, is going to use these pretty quickly so we don't ever build up any product, which keeps our Q less than 1, which we need in order to get our delta G into the favorable range. So the actual delta G is about 0. So this is also a very reversible reaction, which sometimes surprises people. I think the breaking of the carbon-carbon bond seems like this should be like super irreversible. Like once you've done it, you can't go back. But even think about it, it's named for the reverse. So clearly the reverse is something that can happen. So this is irreversible. Sorry, this is a irreversible step. So yeah. All right, so the mechanism, I know this looks a little ridiculous, but if you just kind of follow it through, and these little boxes are actually really helpful because they tell you what's going on. So I'm going to tell you in words, but if you're back studying or whatever, they're going to tell you what's going on. So we've got this ring sugar. The first step is, again, just going to be binding and opening up of the ring back to just our linear sugar here. Second step is going to be a lysine in the active site attacking the carbonyl. Again, generally speaking, if there's a carbonyl there, it's probably going to get attacked as part of their mechanism. So then the carbonyl opens up. Generally, when carbonyls open up, they either stay as O- or they grab a proton, if available, to just make an alcohol. They're just going to be more stable that way. So this is covalent interaction, right? We have a form a covalent bond between the enzyme and the substrate, and we form this tetrahedral intermediate. And then what's going to happen is this base, so this is some other side chain that is basic, so maybe a negative glutamate or something like that. So that's going to deprotonate this hydrogen and form a double bond here. So we're kind of going in the wrong direction. Now we've made a double bond to the substrate, but in doing that, we're going to kick off the entire OH here. So we're actually going to make water. So this sort of a thing, we saw this at the beginning, this is called a Schiff base, where we have this carbon double bound to a nitrogen, a positively charged nitrogen. It should look almost like an equivalent to a carbonyl. All right, and so similarly, we can have things attack that. So now what's going to happen, we're going to have another base over here, deprotonate this OH, forming a carbonyl here. And so this is really the aldol step, or the reverse aldol step. So we're going to deprotonate here, form the carbonyl. That means something has to break. Could be this one, could be this one, but neither of those are going to want to break. But this one can break because we have the Schiff base right here. So this bond breaks. So when you draw electrons coming from a bond going somewhere else, that means the bond is going to break. So this bond breaks. Electrons go up here, make a double bond here, and then these electrons can move from the Schiff base double bond onto the nitrogen. So that's the nice thing about nitrogens. They're positively charged, so you can have double bonds move up like that. So we actually create the first product at that point. Okay, so we create the product that is made from carbons 4 through 6, so the bottom half of that molecule. So this is going to be glyceraldehyde 3-phosphate. So remember, we should know what glyceraldehyde looks like. It's the 3-carbon aldose, and 3-phosphate means that it's phosphate on the third carbon, or really on the third oxygen, the oxygen coming off the third carbon. So that's going to be the first product, but we have this whole rest of it stuck still to the enzyme, and the rest of the mechanisms will be getting that off. So the next thing that's going to happen is we're just going to reform that Schiff base and move the electrons, let the electrons take a hydrogen. They couldn't do it here because it it's just not as favorable. But now we can just bump back down and take the hydrogen. So now we've, again, made another shift base, and we've made an alcohol. So if you look at this, this looks pretty much exactly like dihydroxyacetone phosphate, except that we have this shift base here. So for this class, what I'm just going to say is we can, trust me on this, you can take a shift base, add water, and what that does is it just replaces, you basically just chop this off and you turn it back into a carbonyl. It's kind of just a multi-step reaction, and I don't think it's worth stressing over here, but basically water can come in, attack here, and some stuff happens, but we end up with the carbonyl where on the carbon the shift base was, and then just an amine for the nitrogen. Right, so that makes our second product. So we haven't seen this one before, but you should know what acetone is, right? Acetone is just this. So it's a dihydroxy with OHs on both sides, acetone phosphate. So we don't have to say which carbon it's on because this is a symmetrical molecule. So we could say one, but it's just not meaningful. So dihydroxyacetone phosphate is the smallest ketose sugar. We don't name it as a sugar because we don't. So you should know what this one looks like too. You should know what these molecules look like in glycolysis because most of them we kind of already know or can figure out from the names, but you should know what dihydroxyacetone phosphate is. So now we've made both of our products. Great. And we basically are back. We have to do some moving around of protons to get us back to where we were on the enzyme, but we're not going to worry too much about that. All right, so like I said, overall, it is pretty complicated. I get that. This is going to be the most complicated mechanism, I would say, that we see this term. But if you kind of focus, you can figure this out. I'm not going to make you redo this whole thing. What I do commonly ask is I'll say maybe write the next step. So I might give you this and say draw the next step, or I give you this and say draw the next step. So the dihydroxyacetone phosphate came from the top three, which kind of makes sense because we know that's where the carbonyl is on carbon 2, and the glyceraldehyde 3-phosphate came from the bottom three. So step 5, what we have to do is we want everything to be glyceraldehyde 3-phosphate. So those top 3 carbons have to go through step 5 in order to do that. But if you look at this, these are isomers. It's just this is a 3-carbon ketose. This is a 3-carbon aldose. And so we can isomerize this by essentially moving the carbonyl there. So this is an isomerase. The mechanism of this is essentially the same as the mechanism of step 2. It's reversed, and it's obviously on a slightly different molecule, but really was only the first couple that mattered in there. So the mechanism is basically of step 2, so I'm not going to re-show it to you. This delta G is a little positive, but again, with the Q, it's going to be pretty close to 0, and so this is going to be highly reversible. All right, so now we are starting the payoff phase. So we have step 6 is going to be the oxidation step. So we're going to oxidize glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, and we're going to reduce NAD+ to NADH. So this may not look immediately to you, like we're putting a phosphate on, which usually is not a redox reaction, but we're putting a phosphate on to where there isn't already an oxygen. So if we look at this carbon, it's bound to 2 oxygens, a hydrogen, and a carbon, and now it's bound to 3 oxygens and a carbon. So that's going to be a redox reaction. So we're going to go through the mechanism of this one. It's not as complicated as the last one, but before we do that, this is also reversible. Delta G is pretty close to 0, and the Q will make it go the rest of the way. So we start up here. So we have glyceraldehyde 3-phosphate is going to come in. So here we are. And then a cysteine, a deprotonated cysteine in the active site is going to attack the carbonyl forming our tetrahedral intermediate. And then this O minus is going to collapse down. And here's the somewhat surprising part. We're going to have hydride be a leaving group. Hydride is usually, right, if you have hydride be a leaving group, I think Dr. Stoltz is probably not going to say that's generally okay. But in this situation, the enzyme is holding NAD plus in just the right place. So it doesn't have to go very far. It doesn't really have to be a hydride for very long. And the hydride is going to move on to NAD plus. So we formed this intermediate, of course, where we're bound to the enzyme, but we've now reduced NADH, or we've reduced NAD plus to NADH. Okay, and then at this point, actually, this swaps out for another molecule, but that's really just for resetting for the next mechanism, the next reaction. And now in comes the phosphate, and one of the O minuses can attack the carbonyl, and then kick off the sulfur. All right, so apparently it just couldn't have done this directly, but once we involve the enzyme in here, this works. This is why, enzymes participate covalently, so it can do things like that. So now we formed our 1,3-bisphosphoglycerate. Remember, bis means there are 2 phosphates, but they're in different things. So they're on 1 and 3. So this is 1, and this would be, or sorry, this is 1 and this would be 3. It's sort of drawn, upside down. So step 7 is another phosphate transfer, but this one is simpler because it is just like we've seen before. So this is a kinase. Usually we think of kinases as putting phosphates onto organic molecules from ATP, but enzymes can work in both directions, and in this case, the kinase is going to be doing the other reaction, which is taking a phosphate off the organic molecule and putting it onto ATP. So in this case, it's really that this is one of the O's on this phosphate. It's going to attack here, kick this off. Remember that normally if we take a phosphate off with a phosphatase, which is what we learned did that, we don't put it onto ATP. We would just use water to do that. So it's named as a kinase because even though it's doing the reverse reaction, it's involving ATP and ADP. So this is our first making ATP step. And this one is actually pretty reversible. Again, should kind of make sense since it's a kinase. We can also put it back on. Also, I guess I want to point out here where I'm not writing down that this is happening twice for each glucose molecule, because from the perspective of this enzyme, it's not. It's just doing it normally. But the 2 times is simply so that we can keep everything related to one glucose. All right, step 8 is another phosphate transfer, but it's actually really moving a phosphate. So we have 3-phosphoglycerate, and we're making 2-phosphoglycerate. So essentially we have to take the phosphate and move it from carbon 3 to carbon 2. We actually do not move the same phosphate though. What happens is 3-phosphoglycerate goes on to the enzyme. There are 2 histidines in that enzyme. One of them already has a phosphate on it. And so this histidine is going to deprotonate, which causes this to attack the phosphate. So actually we make a diphosphate, or bisphosphate, 2,3-bisphosphoglycerate for a second, and then this histidine goes, well, I would like the phosphate back, but it takes it from here. And then this is going to take the hydrogen back. So we actually swapped it out. So what it actually gets is the phosphate from the previous molecule that was on this enzyme. But practically speaking, we had a phosphate on 3, and now we have a phosphate on 2. And this one's also quite reversible. Delta G pretty close to 0. Step 9 is a dehydration. So that's taking off of water and forming a double bond. All right. We've actually seen this one before. We saw this in the enzyme chapter. It's called enolase. Right. So we saw this mechanism where the lysine takes off the proton and forms a double bond here. So we have double bond with the 2 O minuses sticking off. And then one of those O minuses collapses down, moves the double bond over here, and kicks off the OH. Right? And we know this glutamate is going to help that by being protonated ahead of time. So this is phosphoenol pyruvate. And I'm going to say the best way to learn what this molecule looks like is to know what pyruvate looks like. And this is called the enol form of pyruvate. And then there's a phosphate on carbon 2. All right, so this one also pretty reversible. So notice that most of them so far have been pretty reversible. And then our final step is just another phosphate transfer with another kinase. So again, now we have this phosphoenol pyruvate. ATP comes in, takes off the phosphate, leaving us with, it actually directly is going to leave us with the enol form of pyruvate, but that is going to tautomerize, which basically it's almost like resonance, but you move a hydrogen in this case. So essentially it's like these electrons move down, and then these electrons come and take this hydrogen. So it's sort of an internal isomerization. So this is pyruvate with our ketone in the middle, methyl and carboxylic acid. But if you just turn the ketone into an alcohol and make a double bond, you just move where the double bond is. That's the enol form of pyruvate, and that's the one that got phosphorylated. But once we take off the phosphate, enol prefers to be in the keto form. So that's the one we usually draw just regular pyruvate as. All right, now this one has a very negative delta G, and this reaction is highly irreversible. This is pretty common. This is the last step, and we want to kind of finish this up, and once we've gone through this, we're not going to go backwards because we haven't had a irreversible step in a while. So if this one was also reversible, you'd have things going back through. But this one is irreversible. Also, we're making these ATPs, so we probably don't want to just like use those up, right? All right, so I just want to point out so many phosphate transfers in there, right? Kinases all over the place and whatnot. And one reason for that is that so that pathway intermediates remain in the cell. We're making some pretty small things, and if they didn't have phosphates on them, they might just be nonpolar enough to go out through the cell, and we don't want to do that. So we're going to everything's going to be phosphorylated, and you can track why certain steps maybe happen at that time, right? So we phosphorylated this one the second time before we broke it, so that by the time when we broke it, we would both step parts would have a phosphate. Also, I mean, we're making ATP, so there's going to be a lot of phosphates there. At that point, so now we've made pyruvate. So this is our glycolysis right here. At that point, pyruvate can actually go through multiple different pathways depending on the organism. So in humans, we have two options. One is under aerobic conditions. We can go to acetyl-CoA and then through the citric acid cycle. This is what we're going to talk about next time. Alternatively, under hypoxic or anaerobic conditions, we can form lactate instead. And we'll talk just briefly about that here. Bacteria and yeast, instead of forming lactate under, or I would say some bacteria and yeast, instead of forming lactate if it's anaerobic, they go to ethanol instead. We're not going to focus on that in this class, but this is, of course, how we get things like beer, and is by fermentation to ethanol. Really any sort of alcohol that you're going to buy that would have come from this sort of thing. But we can't do this. We are going to do this instead. So we're just going to briefly, since we're focused on humans, that's what we're going to talk about here. So that fermentation to lactate is basically going to avoid any oxygen needed to be used. And so if we go through the citric acid cycle and that other middle part, we need oxygen. But the key thing is we need to recycle the NADH because we just don't have very much of it, and we're going to use 2-NADH every time we go through the glycolysis pathway. And if we don't recycle them with pretty quickly in some way, we are going to run out of it. So the real purpose of this fermentation step is not to create lactate. The real purpose is to recycle NADH back to NAD+. All right, and so since we have 2 pyruvates every time, we would make 2 lactates, and we would recycle the 2 NADHs. All right, because this pyruvate to lactate is going to be a reduction, of pyruvate, and so it's going to be an oxidation of the NADH. So essentially, we can essentially go from glucose to the pyruvate to the lactate without having a net change in our NAD+ concentration. However, this is something that we can only do for a short period of time. Humans can really only use our muscles anaerobically for maybe 15-20 seconds or something max. So it's not something we can do very long, but we can do it in sort of bursts of speed. All right, so in the next video, we will move on and talk about the aerobic pathway to deal with pyruvate.